class. And this week we're talking about what I consider to be some of the most interesting stuff in the course. But with that said, I also want to warn you that this is also some of the most difficult stuff in the course. Now, the good news is once you get past this, everything after this is a lot more straightforward and a lot more simple. But with that said, make sure that you really devote some time to this particular module this week, because what we're going to be talking about this week really does set the framework for some really important concepts that we'll be talking about in a few weeks, specifically when we talk about severe weather, thunderstorms, hurricanes, and all the interesting stuff that a lot of students really enjoy. So even though this might be a little tough and a little bit theoretical, I promise you there's some really cool meaning behind this, and we're going to actually learn some pretty interesting things in this module. So just make sure that you give yourself the time that you need, and let's jump in. So this module has a few really key goals. The first key goal is to understand how air behaves as it rises. Now, if you remember from previous modules, we've talked about the fact that air expands and cools as it rises. And we also know that it condenses as it rises. But how quickly does it expand and cool? How quickly does condensation happen? How does condensation affect the behavior of rising air? How does this all affect the development of clouds? And does this really matter in our everyday, day-to-day life? Believe it or not, the answer to that last question is a little more straightforward yes than you would think. Believe it or not, the overall structure or the overall behavior of our weather is actually really dependent on what we're going to be talking about this week. I also want to explain the difference between a stable and an unstable atmosphere. And then I'm going to talk a little bit about that stuff that falls from the sky. I'm talking about rain, snow, sleet, hail, all those interesting things. How do they form? How do they fall to the ground? So that's what we're going to be talking about this week. So without further ado, let's jump in. So this first lecture is going to deal with something called adiabatic cooling. And this is just a fancy term that we use to describe how air cools as it rises. So let's talk about it. So first off, to know what an adiabatic process is, there's a few other words that we need to quickly explain. The first one is the term air parcel. Then we're going to talk a little bit about what adiabatic itself actually means. And then we're going to talk about what are called lapse rates. So definitely make sure that you pay attention to these next few slides, write these notes down, and obviously send me emails if you have questions. So let's first talk about what an air parcel is. So think of a balloon, like the one on the right of your screen right now, like this one right here. Well, believe it or not, an air parcel is basically like a balloon. And the way that air parcels work is rather than treating the atmosphere as one gigantic individual blob of air, meteorologists actually treat the atmosphere as trillions and trillions and trillions of these little parcels of air. And these parcels have a few really key rules to them. Specifically, we treat these parcels as completely independent and isolated from their neighbors. Meaning they do not interact with one another, they do not exchange anything with one another, they don't share anything, they are completely isolated from one another. And I like to call this the Las Vegas rule. What happens in the parcel stays in the parcel. Just like the old statement for Vegas, what happens in Vegas stays in Vegas. Well, what happens in these air parcels stays in the air parcels. There's one exception to this that we'll talk about in a couple of lectures when we talk about what's called the rain shadow effect. But for the purpose of the next two lectures, this is good enough for right now. So the parcel doesn't exchange anything with its outside world. Now let's talk about what would actually happen to this parcel as it rises in the atmosphere. Well, as it rises in the atmosphere, it is not exchanging anything with its surroundings. Again, it's like Las Vegas. However, as the parcel is rising, air pressure is decreasing. This causes the parcel to expand. The same thing would happen if you bought a bag of chips and then drove them up to Lake Tahoe. You'll notice that as you're driving up, the pressure is decreasing outside. You'll feel your ears pop. And one of the things you'll notice is that bag of chips starts to swell a little bit. And this happens because of that lower air pressure. Well, something else is happening to the air inside that bag. As the air is expanding, this forces it to cool. And the reason why that happens is because work is being done on the parcel as it's expanding. That work requires energy. That energy is spent in the form of heat, hence the parcel cools down. The same thing happens if you've ever used a can of hairspray and you've sprayed it. The air inside the canister is very, very compressed. Well, as soon as it shoots out of the canister, it expands quickly and it feels really cold. If you've ever sprayed hairspray on your hair, it feels really cold. Well, the same thing happens with air as it rises in the atmosphere. There's many different types of parcels. And we as meteorologists treat anything as an air parcel, but a few good examples, convective thermals. So we've talked about in Module 2 how when you have a really warm bubble of air near the surface, it'll rise, very similar to the bubbles that are rising in a pot of water. Those are examples of air parcels. You can treat those bubbles as individual air parcels. Or smoke rising from a fire. That smoke is made up of trillions and trillions of these little air parcels, and they rise. Or particles of air pollution. So things coming out of the tailpipe of your car, any kind of air pollution near the ground, those are types of air parcels as well. Now, as I just mentioned, if we release an air parcel into the air, it expands and cools. Again, this is because air pressure declines as you go up in height. And then the opposite is true if a parcel sinks back down. The parcel will contract and warm. So as the parcel rises, it expands and cools. As the parcel sinks, it contracts and warms. Now, with that said, the cooling process is what we call adiabatic. But what does adiabatic actually mean? Write this down. Make sure you double underline this. Guaranteed you'll see this on a quiz or test or something in the future in this class. What adiabatic simply means is it's heating or cooling inside a process or inside a parcel due to solely the expansion or contraction of the parcel. What this means is that there is no heat exchanged with the outside environment. So adiabatic cooling is cooling that is caused solely by what's going on inside the parcel. So in the ambient atmosphere, you have radiation heating things up. You can have advection moving air masses from place to place, and all of those things can influence a parcel's temperature. But in the case of adiabatic cooling and adiabatic warming is just a parcel of air warming as it sinks. In the case of adiabatic, there is no exchange of heat with the outside atmosphere. Now, this isn't 100% the way things work. With that said, if we did take into account those exchanges of heat, which are all relatively minor, that would create a much more complicated situation, and it would be something that would be a lot harder to deal with, and there's very little benefit for doing it. The accuracy, the improvement in accuracy of our weather models, of our forecasting, isn't worth the extra computational time and the extra energy that would go into adding heat into the process. So we stick with adiabatic. So, and again, it's an approximation. So adiabatic processes simply occur when a parcel of air does not exchange heat with its outside environment. Instead, only one of two things affect the temperature of the parcel. The first one we already mentioned, either expansion or contraction of the parcel. And this is the main thing. As the parcel rises, it expands, that causes cooling. Again, just like the hairspray that comes out of the canister. On the other hand, if the parcel is sinking, it's contracting, and that causes warmth. But there is one other thing that can happen. If you have a parcel of air that is near saturation and it rises, the amount of water vapor in the parcel doesn't change either. Again, like I said on a previous slide, the parcel is like Las Vegas. What happens in the parcel stays in the parcel. So there's no real additional, there's no real water vapor being taken away or being added. So the amount of water vapor stays the same. So the dew point temperature should, for the most part, stay the same. Now, it's going to cool a little bit. We'll talk about why in a few minutes. But for right now, water vapor content stays the same. However, as the parcel's rising, it's cooling. And as it cools, it approaches the dew point. Eventually, it reaches the dew point, and condensation begins to happen. Condensation releases latent heat. Latent heat then warms the parcel up. So the latent heat released by a parcel or by moisture as it's condensing can affect the temperature of the parcel. And we're going to talk about each one of these two processes in detail in a few moments. So as an air parcel rises, it expands and it cools. Now, if the air parcel is unsaturated, meaning that the air temperature is greater than the dew point temperature, therefore the air parcel is unsaturated, we say that the parcel will cool dry adiabatically, meaning there's no condensation happening, and therefore the parcel is only cooling due to expansion. When this happens, we have a set rate for it, and I'll talk about that in a second. On the other hand, if the parcel becomes saturated, meaning the temperature reaches the dew point, the parcel still rises, it still expands, it still cools, but that condensation releases latent heat. Now, the latent heat isn't enough to fully offset the cooling, but it does offset it slightly. And therefore, the parcel is still cooling, but it's cooling at a slower rate. We call this moist adiabatically. Now here's the good news. The good news is we actually have a set rate for how much these parcels cool. So there is a set rate. There's no mystification behind this. As a parcel rises, it cools at this set rate. And the rate is determined solely based on if the parcel is saturated or not. If the parcel is saturated, we say that it cools dry adiabatically. Or sorry, if the parcel is unsaturated, I lied. If the parcel is not saturated, if it's unsaturated, it cools dry adiabatically. And the rate that it cools at is 10 degrees Celsius per every 1,000 meters. So all that this means is if the parcel is unsaturated, as it rises, it cools 10 degrees per every 1,000 meters. So if it's unsaturated, it cools 10 degrees per every 1,000 meters. Now, if you prefer to use imperial units, 55 or 5.5 degrees Fahrenheit per every 1,000 feet, for the purpose of this class, we're going to stick with the metric units, mainly because they're a lot cleaner. They're a lot easier to calculate. So every 1,000 meters you go up, you knock off 10 degrees Celsius. Another 1,000 meters, knock off another 10 degrees. Another 1,000 meters, knock off another 10 degrees, and so on. So for example, let's say we have an air parcel at the surface, and it has a temperature of 30 degrees Celsius. As it rises, it expands and cools. Goes up 1,000 feet, it cools 10 degrees. So now it's 20 degrees Celsius. Go up another up another 1,000 feet, or up another 1,000 meters. Sorry, again, bloopers in the video. Up another 1,000 meters, it cools another 10 degrees. If we went up another 1,000 meters, it would cool another 10 degrees, and so on and so forth. So as the parcel is rising, it will continue to cool at a rate of 10 degrees Celsius per every 1,000 meters. Now what about a moist parcel? So a moist parcel is going to cool at a different rate, and we'll talk about that in a second. Now if you're like me, I like to draw pictures. It's really nice to draw a picture of a parcel of air at the surface, and then rise it to 1,000 meters, and draw another little bubble, and write in the new temperature, and then go up another 1,000 meters, and just keep counting as you go up. Up 1,000, subtract another 10. Up another 1,000, subtract another 10. And this works very well if you're comfortable with this. However, if you're a very numerical person, if you've taken Algebra 2 or Pre-Calculus or Calc 1, if you've taken many more numerical classes, you might be a little more comfortable using an equation. Well, there's actually a really simple equation that we can use to calculate adiabatic cooling. So here's how you would do it. So you would start with a known temperature, specifically the temperature at the surface. For this previous situation, the temperature at the surface was 30 degrees Celsius. So right here, you would say that the temperature is, forgive my very poor drawing here, 30 degrees Celsius. And if we wanted to find the temperature at, let's use a height of 2,000 meters. So like this, 2,000 meters. All we would have to do is we'd have to take our 30 degrees Celsius and subtract from it a simple calculation that's simply the product of the lapse rate times the height. So we know the height is 2,000 meters, and we also know that our lapse rate is 10 degrees Celsius per every 1,000 meters. And there we go. So 10 degrees Celsius per every 1,000 meters times 2,000 meters. Let me put the other parentheses here. Now remember, just like in your math classes, you're going to follow the order of operations. Do what's inside the parentheses first. So 10 over 1,000 times 2,000. Now we would have a situation where we have meters divided by meters, so these cancel out. In that case, we're just canceling out units. 1,000 times 2,000, so 1,000 goes away. That just becomes a 1. And then 2,000 goes away, that just becomes a 2. So we just end up having 30. Oops. 30, that's 30. Let me use an eraser there. It erased the whole thing. Let's try that again. Looked like an 8. 30 minus 20, which equals 10. 10 degrees Celsius. So using this formula, if you're comfortable with it, is also another easy way to calculate adiabatic cooling. But if you're not comfortable with using the formula, counting is just fine. Again, 30 degrees at the surface, 20 degrees at 1,000. Every 1,000 you go up, subtract another 10 degrees. And here's an example of this. I will leave you to do this example, and if you want to get a response, or if you want to know how things are going, or if you want to know what the answer is, you can ask me. But let me just give you a hint. Every 1,000 meters you go up, subtract 10 degrees Celsius. And using that formula right there, again, temperature at 4,000 meters equals the temperature at the surface minus lapse rate times height. Plug in the numbers, and there you go. If you want to know a little bit more about how we got to this answer, again, please email me or stop by my office hours. And there's your answer. Now, what about moisture in the parcel? So I kind of gave the hint already that these parcels have atmosphere in them. And remember, up to 4% of our atmosphere is water vapor. And so there's moisture in the parcel. Well, as the parcel of air rises, that moisture may condense. Why? Because the parcel is getting cooler and cooler and cooler. So the temperature of the parcel is approaching the dew point. And since the temperature of the parcel is approaching the dew point, saturation may occur. If saturation occurs, latent heat is going to be released. And if that latent heat is released, that then changes the cooling rate. We'll talk about that in a second. But before we do, I do want to mention that as the parcel rises, air pressure changes. And since air pressure changes, the dew point temperature changes as well. And the dew point actually changes at a rate of 2 degrees Celsius per every 1,000 meters. Now this is complicated because now not only are we watching the parcel change, but we're also watching the dew point change. So for every 1,000 meters you go up, you're subtracting a temperature from the parcel, and then you're subtracting 2 degrees from the dew point. With that said, if you have a saturated parcel of air, let's say you start with a parcel at the surface and it rises, that parcel is now going to cool at a new rate. Why? Because water vapor is condensing, clouds are forming, and latent heat is being released into the parcel. This results in a slowdown of the cooling. Rather than cooling at 10 degrees Celsius per every 1,000 meters, the parcel will now actually cool at 6 degrees Celsius per every 1,000 meters. Well, Terrence, where did the other 4 degrees go? Well, they were offset by latent heat release, so I'm glad you asked. So now the parcel is cooling moist adiabatically, and it's cooling at a rate of 6 degrees Celsius per every 1,000 meters. So rather than cooling at a rate of 10, it now cools at a rate of 6. So using that equation that I showed a moment ago to determine the temperature of a parcel, we just use that simple equation again. The temperature at a given height equals whatever the temperature was at the surface minus this right here, the elevation times the lapse rate. Another example right here. I'm not going to go through it since I've already gone through a few, but if you would like to pause and take a look, another example here, again, you're just looking at the temperature at your given height, the temperature at the surface, minus that change in temperature. Now, let's actually do a couple of examples of all of this, just to review. So let's suppose that the air inside a parcel is really dry, and that parcel is actually smoke from a fire. As the parcel rises, its surface temperature is 60 degrees Celsius. What will its temperature be at 1,000 meters, 2,000 meters, and 10,000 meters? Well, using our equation, the temperature at a given height equals the temperature at the surface minus the rate times the height. This is what we get. At 1,000 meters, the temperature equals 60. Again, the temperature at the surface minus the rate, which since it's dry, it's cooling at a rate of 10 degrees Celsius per every 1,000 meters, times the height, which is simply 1,000 meters. And voila, the result we get is 60 minus 10, which equals 50. Again, 60 degrees Celsius is the surface temperature. The rate of cooling is 10 degrees Celsius per every 1,000 meters. The height is 1,000 meters, so these actually cancel out, and all we're left with, 60 minus 10, which is 50. If we go up to 2,000 meters, the only thing that we change is the height. So now instead of going up 1,000 meters, we've gone up 2,000 meters. Again, these cancel away. All we're left with is 10 degrees Celsius times 2, which equals 20. So 60 minus 20 equals 40. And then at 10,000 meters, at 10,000 meters, again, all you change is the height. And what you get here is the thousands go away, the meters go away. All you're left with is 10 times 10. So 60 minus 10 degrees Celsius times 10 equals 60 minus 100, which equals minus 40 degrees Celsius. So that's all that you have to do. So it takes a little bit of work, but once you get the hang of it, it's like riding a bike. Now what about, let's suppose instead that the parcel is moist. So now the parcel is moist. So there's steam in the parcel, the air is really moist, everything is saturated. However, everything else remains the same. The surface temperature is 60 degrees. We're still looking at 1,000, 2,000, and 10,000. You would use the same equation. The only thing that would change in this scenario is the rate. Instead of using a rate of 10 per every 1,000 meters, you would use a rate of 6 degrees Celsius per every 1,000 meters. That's the only thing that would change. And so plugging everything in, but just now using the different rate, at 1,000 meters, you get 60 minus 6 over 1,000 times 1,000. Again, the thousands go away. So you just get 60 minus 6, 54. 2,000, 60 minus 12, 48. 10,000, 60 minus 60 equals 0. Again, take some time if you want to sort of go through this. Pause this video if you really want to. And if you have any questions, please, again, email me or drop by my office hours. Now, the last thing I'm going to talk about for this module, and the most sinister thing, is in most cases, as a parcel rises, it doesn't start out moist. And in most cases, as a parcel rises, it does become saturated. So, what happens to a parcel as it becomes saturated as it rises? So if it starts dry, what's going to happen to the parcel as it rises? Well, it's going to keep cooling. Eventually, it reaches the dew point temperature and becomes saturated. Well, take a moment and ask yourself, if the parcel becomes saturated as it rises, is it going to continue to cool dry adiabatically, or is it going to switch over to moist adiabatically? Well, the answer is, first off, clouds form. And we switch from dry adiabatic to moist adiabatic. For example, let's say this is from the textbook, this is figure 9. I cut out some irrelevant stuff that's going to be talked about in the next lecture, but for right now, this is all you need to know. So at the surface, we have a parcel. Sorry, trying to get my cursor to appear. We have a parcel at 30, and it's unsaturated at 30. The book didn't mention this here, but the dew point was 22 degrees Celsius. So at the surface, the dew point was 22 degrees Celsius. I'll actually write up here dew point. Actually, I'll just put dew and P for point. So the dew point at the surface is 22 degrees Celsius. The temperature of the parcel is 30. As you go up 1,000, the temperature cools to 20 degrees Celsius, and the dew point cools to 20 degrees Celsius. Again, the dew point cooled 2 degrees Celsius per every 1,000 meters because of changes in pressure, whereas the temperature of the parcel cooled 10 degrees Celsius because it was dry adiabatic. However, once the two equal each other, once the temperature and the dew point equal each other, you now have saturated air. So now you switch from the dry rate to the moist rate. So when the parcel becomes saturated, you switch from the dry rate up to the moist rate. And when this happens, this level at which it happens is what we in meteorology call the lifted condensation level. So it's at that level that we switch from dry to moist. It's at that level that the parcel becomes saturated. And believe it or not, it may seem hard to calculate, but if you walked outside right now, you could find the lifted condensation level very easily. Here's how. If you look at the base of any cloud, the base of that cloud is the lifted condensation level. Air below that height was not saturated, hence you don't see any condensation. But at the base, the parcel has become saturated. So it is now the lifted condensation level. So now the last thing I'll mention for this lecture before I stop is let's actually figure out how to figure out the lifted condensation level. So let's suppose we have a parcel of air at the surface with a temperature of 40 degrees Celsius and a dew point of 16. How would you figure out its temperature as it rises? How would you figure out the lifted condensation level? Make sure you pay attention to this. If you want to take a little break right now, hit pause and then come back. Otherwise, let's talk about this. So, first off, you need to ask yourself, is my parcel saturated? Well, here's how you can figure that out. If the temperature of the parcel is greater than, I'm going to put a little arrow or one of those little greater than signs. If the temperature of the parcel is greater than the temperature of the dew point, you have an unsaturated parcel. The parcel is warmer than the dew point, so the air is unsaturated. If the air is unsaturated, as it rises, it's going to cool dry adiabatically. Okay? It's going to cool dry adiabatically. All right, so let's do this. If you go up 1,000 meters, since the parcel is unsaturated, you're going to subtract 10 degrees. On the other hand, for the dew point, you're going to subtract 2 degrees. So you subtract 10 from the air parcel, 2 from the dew point. And then ask yourself the question again. Is the parcel warmer than the dew point or equal to the dew point? If the parcel is warmer than the dew point, then it's still unsaturated. You keep going up using the same procedure. So we go up another 1,000 meters, take away another 10 degrees. And, whoops, there's a little typo here. Easy fix. And let's try that again. Okay, so you go up 10 degrees and you take off another, you go up 1,000 meters, you take off another 10 degrees, and then for the dew point, you take off another 2. So now at 2,000 meters, the temperature is 20, the dew point is 12. Again, temperature is warmer than the dew point, so it's still unsaturated. And then look what happens at 3,000 meters. At 3,000 meters, the temperature and the dew point are now equal to each other. This is the lifted condensation level. At this point, you switch over to the moist rate, and then you proceed on after that. So at 4,000 meters, now instead of cooling at 10 degrees Celsius, you're now going to cool at 6 degrees Celsius. So if you want to go up another 1,000 meters, now we're going up to 4,000 meters, you subtract 6 instead of 10. And then going up another 1,000 meters, you subtract another 6. And you keep subtracting 6 as you go up. Now there's one thing you might have wondered here. Well, wait a second, Terrence. What happens to the dew point? Well, once moisture begins to condense, that causes the dew point to drop even more. And in fact, the dew point will now drop in tandem with the air temperature. So as the parcel rises, the dew point will cool down at the same speed as the air temperature after it's become saturated. So before it becomes saturated, it's 2 degrees Celsius per every 1,000 meters. After it becomes saturated, the dew point will always equal the air temperature because that's what saturation is. Now there is something called supersaturation. We're going to talk about that for a very brief second in a couple of lectures. But that'll be a ways from now. So now I have one more question to ask you. What happens, or what even allows air to rise? How is air even able to rise? Well, we're going to talk about that in the next lecture. So until then, I'm Terrence Mullins. Thank you for watching.